Hi everyone, and welcome to my presentation titled A New Ecosystem for Terraform Provider Code Generation. My name is Brian Flad, and I'm a staff engineer at HashiCorp, working in the Terraform ecosystem group. I've been with the company for over 5.5 years. Previously, my role was engineering lead with the Terraform Provider for AWS, and now my role is on the Terraform Development Experience team, helping build foundational code and tooling for Terraform integrations, such as providers. My team and I are very excited to discuss for the first time publicly about one of our long-term projects to better scale the Terraform Provider ecosystem through code generation. This talk is intended for those building or interested in building Terraform providers. And with that, let's get started. The agenda for today's talk, we'll start with some background of how Terraform interacts with APIs. We'll talk about some of the challenges and realities to creating these integrations. We'll walk through a proposed solution and design. Then we will show a prototype and some of the next steps of the future. So let's dive into the background of Terraform and its providers. But we can first start with the context of HashiCorp products as a whole. HashiCorp products typically enable application development teams and platform teams to work across a broad range of infrastructure services. Today's topic, though, is about Terraform itself. Conceptually, Terraform provides workflows that enable practitioners to write a declarative configuration which describes the resources they wish to manage in their infrastructure services. These might be virtual machines, disks, or other infrastructure components. This happens by Terraform reading the configuration, generating a graph of operations, then calling an API, which actually performs those operations in the infrastructure service. The concepts in the middle represent the interface between the practitioner and their desired infrastructure. This is where the magic happens with Terraform. Now, creating and maintaining a single product or code base that would implement all potential APIs would be quite difficult. There are thousands of infrastructure services available today. To enable better extensibility, Terraform has the concept of a provider plugin. Its role is enabling configuration which ultimately calls those services. Providers are a collection of managed resources and data resources. Managed resources handle a single infrastructure component with a full management lifecycle such as creation, updates, and deletion, while data resources are read-only sources of information about infrastructure components. Ideally in this design, a provider is focused on a single API, and resources are aligned with the terminology of the service. This is intentional as it offers benefits to both practitioners and developers of these integrations. Only a single domain of expertise is needed, the service itself. For practitioners, it also means that there is a centralized handling for connectivity and authentication to a service. For developers, it also means that there's no need to create abstractions for multiple resources or across services. Those abstractions can be handled elsewhere through Terraform configuration functionality, such as Terraform modules. If we look at the diagram again, it still appears to be a little ambiguous. How exactly does a provider implement both Terraform concepts and the logic to call APIs? If we expand the diagram a little, there are some new pieces to the puzzle. There are software development kits, or SDKs, that relate to both Terraform and the API. Developers combine these two SDKs to create the provider code. Let's talk about the Terraform side of this first. A Terraform SDK is the provider code component which is responsible for building logic for Terraform's concepts. Between Terraform and providers is a protocol which defines all the operations and data that can pass between the two. Collectively, these protocol operations are bundled together into a higher level abstraction created by the Terraform SDK, such as the provider's definition of a managed resource or data resource. On the other side of things, specifically the data, the Terraform SDK bundles together higher level abstractions of what data is and how it gets represented in code. whether it be the concept of a schema definition, which describes the structure and types of data, or a type system to read and write that data. If we look a little deeper into what goes into developing a provider resource as it relates to the end goal of communicating with an API, there are some more important concepts. There are the expected bits, such as defining a unique name for the resource, but the more interesting bits deal with defining a schema and operational logic. A schema does a lot of heavy lifting for a resource. It describes a shared shape of configuration, plan, and state data for Terraform. It also must account for any oddities or normalization that might be required between the naming and shape of a desired configuration for practitioners, API request data, and the API response data. On the operational logic side of things, there's the overall mapping of API operations to whatever resource is being created, read, updated, or destroyed. Then within each of those, there's the reading of Terraform's schema-based data, converting it to the data types used by the API SDK, actually calling the API operation, then any necessary conversion and writing of Terraform schema-based data. HashiCorp today offers 3 SDKs for Terraform, as shown here. Terraform Plugin Framework is the most recent iteration of Terraform SDK, which supports all of Terraform's provider functionality available today, and is recommended for all new provider development. Terraform Plugin SDK is the prior iteration, which works okay and is well used across the ecosystem. However, it's lacking some functionality and imposes certain provider behaviors which cannot be easily controlled. Last is Terraform Plugin Go, which generally most developers do not need to know about, but it is a lower level abstraction and can be helpful in some very advanced use cases. In addition to the SDKs themselves, there are a lot of HashiCorp and community-owned projects which can help simplify provider code, automate documentation, and run testing. One of my favorites in this list is Terraform Plugin Mux, which can be used to iteratively migrate a provider code base from Terraform Plugin SDK to Terraform Plugin Framework. In any event, that describes the Terraform side of provider code. Let's switch our attention to the API side of provider code. Much like Terraform having an SDK that codifies its concepts, APIs have a similar notion. API SDKs are a native programming language interface to the API. These generally exist because it would be a huge burden on developers wanting to communicate with an API if they needed to take generic programming language constructs, such as an HTTP client, and manually develop all the necessary parts and bits to successfully make API calls. These API SDKs typically involve an API client, functions for calling API endpoints, and types for all the request and response data. So that describes some background on the provider code and SDKs that are used to develop it. It might be helpful now to take this diagram and flip it on its side. This now describes the manual provider code development workflow. A provider developer combines the available concepts of their Terraform SDK and API SDK to write provider code. There's one last piece before we move forward, though. Some APIs are developed using an API specification or API definition. This can generally directly influence the design of API SDKs and can be used to deploy an API. API specifications, or more generically, interface definition languages, are ways that API developers can automate some of their work. They typically provide their own abstraction concepts, behaviors, data modeling, and potentially API SDK generation. Some examples of API-focused IDLs include OpenAPI specification, protocol buffers, Smithy, and TypeSpec. Each of these has its own terminology, concepts, and project goals. But if we look back at our manual provider development flow, you might notice that there's an interesting disconnect between those API specifications and provider developers. Now, it'd be great if every developer could easily create and maintain a Terraform provider for every API, but let's talk about some of the realities or challenges that HashiCorp has noticed as the ecosystem has grown. The first reality is that APIs support more than just Terraform providers. Many API services support a multitude of API clients, where a Terraform provider is just one integration. This has some potentially unexpected consequences, though. The API may define components which don't align to Terraform's resource model, such as implicit resources that cannot be created or destroyed, only updated. The API may define operations which affect multiple resources. The API's data handling may not match Terraform's data model, which has consistency rules such as state values must exactly match its configuration value. Also, an API may not define errors well enough for Terraform's purposes, such as returning an unauthorized error instead of a missing resource error. Any of these are a barrier to a high-quality Terraform provider today. A second reality is that developers support more than just Terraform providers. While there are dedicated provider developers in the ecosystem, it is generally uncommon. With that perspective, there may be developer unfamiliarity with Terraform concepts, its SDKs, the Go programming language which those SDKs are written in, and potentially other provider quality features such as documentation and testing. Any of these are also a barrier to a high-quality Terraform provider today. Another reality is that the existing provider ecosystem is both broad and deep. For example, there are over 3,000 providers in the public Terraform registry and many more in private Terraform registries. Out of those, there are over 250 providers in the public Terraform registry, which are participating in the Terraform integration program. There is an amazingly wide variety of services and the technology industry represented by these providers. This entails everything from cloud computing, networking components, database management, and so much more. Did you know that you can order pizza through Terraform? That's a story for another time. But if you look at the raw metric such as provider downloads, it's measured in the billions. Clearly, providers are giving practitioners some value. Another interesting aspect is how deep some of these providers are integrated with their services. The AWS, Azure, and Google providers, for example, have almost 4,000 resources under their umbrella. Wow. Another fun reality is that Terraform provider code is often repetitive. However, repetitive code is both a feature and a bug if we dive deeper. Consistent and repetitive code can be boring, but it does tell us some information about our domain. One way to look at it is that APIs tend to follow certain conventions, which is great for consistency. It's less great when code is being manually developed, though, and especially when there's external contributors. These can cause issues such as inconsistent schema definitions, where developers may omit certain attributes or miss certain documented validation behaviors of an API. Inconsistent data handling, where developers may duplicate or incorrectly modify similar code. Inconsistent error handling, such as missing resource state removal on read when an API returns that type of error. And other code duplication, where introducing functionality is considered more important than the maintenance burden. Out of that list, though, it is especially important to call out that valid schema definition and data handling is critical to a successful resource implementation, but it also requires a high amount of effort, and a lot of that effort tends to be replicated or duplicated code. Now, there are certain solutions available to provider developers dealing with these code consistency issues. Sometimes it's possible to create code helpers or packages to deduplicate the code, as with any programming language code. Another option is implementing static analysis or linter tooling that can enforce coding standards and guardrails. In some cases, provider developers may have even gone down the road of code generation. You'll note, though, that all of these solutions tend to be very specialized. Which leads us to our last reality to be discussed today. Specialized code and tooling does not scale. However, specialized code and tooling is required to scale. That last point there is an interesting dichotomy. Most solutions we have seen in the ecosystem have tended to be for specific use cases, such as provider code generator included with a single provider code base, based off of that specific API's conventions and behaviors baked in, instead of a more generic solution that could help the ecosystem more broadly. What if we could reduce or solve these challenges for developers by introducing a more generic solution? Before we try to design that solution, though, let's discuss some of the proposed requirements for that solution. First up would be adaptability. HashiCorp has a long-running adage about its products promoting workflows over technologies. This feels highly applicable in this case. For starters, the technology ecosystem is constantly evolving and improving. With that evolution in mind, some of the relevant details that would affect our solution here is that both API and Terraform concepts, development practices, and tools will change over time. It may be easier to think about this in the sense of technologies or functionalities, but the development model changing over time is likely more pertinent or likely to occur. For example, with a company that maintains its own provider, lowering the maintenance burden may become a business priority, which may lead to more desire for automation than before. Another piece of this is that it would be unreasonable for one technology, whether existing or created as part of this solution, to solve all the issues forever. The solution will need to evolve with everything around it. A next requirement would be extensibility. The existing provider ecosystem is done well because it is extensible. There's not one centralized group of provider developers making the ecosystem a success. Additionally, many providers and provider tooling is also open source, which means that there's an accessible corpus of prior art, example code, etc. when encountering a development situation. An extensible solution should also account for foundational blocks being more helpful than a prescribed solution. With foundational building blocks, it is still possible to build a specialized solution. It may be more effort initially, but it will pay dividends in the long run. Another aspect that is that designing an interface can reduce the required knowledge on each side of the problem domain, while also increasing consistency. And this is due to the introduction of a shared language. Last but not least, the solution should account for the fact that designing an interface can be generic while also enabling specialized use cases. This kind of ties up to what we were talking about before. A final requirement would be usability. As mentioned before, the provider ecosystem and broadly speaking, the API ecosystem already exist. A solution should account for both new and existing provider use cases. Or more concretely, this means lowering the barrier of entry for creating new providers and reducing maintenance for existing providers. The solution should also account for new and existing provider developers. This means lowering the barrier of entry for new developers, such as making it easier for them to be more successful, and enabling existing developers who provide more practitioner value. Additionally, the solution should account for the existing technology gap we already discussed earlier, where API specifications have a wealth of useful information. Now, with our proposed requirements ready, let's start designing a solution around those requirements. This proposal is based on the idea that we can design scalable code generation that meets developers where they're at. If you haven't guessed already, the proposed solution can be summarized as creating an interface. It will also include some other starting pieces. From a high-level view, the following workflow is being introduced. On one end of it, there is various sources of information, and on the other end is provider code. In the middle is our generic interface, and it is surrounded on both sides by specialized tooling on that interface. Now, while these diagrams will show the individual components of the workflow, I do want to note up front that these components could be bundled together as desired. As shown here, there's nothing preventing the creation of a single developer tool that simplifies the process from source to generated code. If we take a deeper look into how these components might operate, you'll notice that we have some of our components from before. A source generator or converter may accept API specification and/or API SDK information. On the other side, the provider code generator is based on a Terraform SDK. Currently, we are going to call the interface the provider code generation specification. I'm sure our marketing folks could improve that naming. Anyway, it's designed to be a versioned interface between one or more sources and one or more consumers. It's intentionally programming language agnostic, source agnostic, and consumer agnostic. It does, however, need to be tailored for a problem domain, which is specific for Terraform providers. Also, while it initially may be focused on code generation, it could theoretically be extended for other use cases as well, which I'll mention shortly. The specification information can be filled in with one or more sources. One valuable source would be an API specification, such as OpenAPI, since typically the API SDK information can also be determined at the same time. If that's not available, another potential source might be parsing the API SDK code itself, which could be very tricky, but technically possible. A helpful source might be a developer scripting or manually filling in the specification information. This might sound like moving the manually developed code problems around, but we'll discuss some of the valid reasons for this. And if you're into the current technology hype, trends, maybe a large language model could help. Also, maybe somebody will make a website for designing a provider. Plus potentially more. Don't let this list stop you. On the flip side, the specification information can be handled by one or more consumers. The main focus is provider code generation initially, but the specification could also help with documentation and testing generation in the future, if that makes sense. Now, from the developer perspective, each one of the components can become a configuration point. Maybe the source conversion generates all potential resources, while only some are desired in the provider code. Maybe the source conversion is not fully correct or includes generic API schema descriptions instead of those tailored for provider documentation. A developer might also be stuck in a situation where there is no source conversion available, only the API SDK. In this workflow, the developer can opt to fill in the specification information. This affords them the ability to get consistently and correctly generated provider code. Especially in larger providers, this might be the starting workflow for introducing the code generation to begin with. And finally, in an effort to be the most flexible, this solution does not prevent the manual code development workflow we discussed initially. While this should hopefully diminish over time, some resources may not work well at all with code generation. This workflow should stay out of the way in those situations. This all sounds great in theory, but let's discuss the proposed solution with real-world workflows and data. To do this, we can take a common scenario and try to provide immediate developer value with a prototype. The main focus of our prototyping effort was schema and data handling, since it could provide the most immediate value. Starting from the high-level workflow, we opted to swap out each of the loosely defined components with real-world implementations. These included OpenAPI specifications as the source, the creation of an OpenAPI to provider code generation specification converter, and the creation of a Terraform plugin framework provider code generator. For the OpenAPI side, we created a CLI and Go module that was able to validate and parse OpenAPI specification and generate the majority of schema definitions and validations. Since OpenAPI does not have Terraform's concept of a resource, the prototype accepts a configured Terraform resource mapping of the API paths and operations that should be associated together in a single resource. For the provider code generation specification itself, the prototype supports the concepts of provider, managed resource, and data resource definitions, schemas within those, all schema types and nesting, associating API SDK types to the schema types, and various other schema functionality. For the provider code generation side, we created a CLI and Go module that creates Terraform plugin framework code. Its usage can be tailored, such as individually selecting what resources and what parts of those resources to generate. The main functionality supported was generating schema definitions and data model types. To briefly see some of the prototype artifacts, here is the pet store example OpenAPI specification, which defines an API with endpoints for managing pets and orders. In our prototype testing, we also used real-world OpenAPI specifications from our friends at GitHub and Scaleway. Here's the prototype OpenAPI conversion configuration, which defines the mapping of API paths and operations to Terraform resource operations. The OpenAPI converter collected all of the API request parameters and API response contents to create a merged resource schema in the provider code generation specification. Then the framework code generator was ran, and it generated a Go code file with a package, name, imports, and schema code. Hopefully you can see the direction we're heading. So, what are our next steps here? We are targeting a technology preview release of our prototype components for HashiConf later this year. Before then, though, we'd love some early feedback from partners and customers. If you're a part of the Terraform integration program, please reach out to your HashiCorp Partners or Alliance contact for additional information. If you're a customer developing private providers, please reach out to your HashiCorp account manager. Thank you for watching, and hope you enjoy the rest of the sessions. Please reach out with any questions. We would be happy to answer them.